We are studying solidification time for casting, and a couple different kinds of casting that we're looking at are sand casting and die casting. So let's look first at sand casting. The equation for solidification in sand casting relates to Shavoranov's rule and generally is given by the expression T, solidification time, equals B, V over A to the N, and we're going to usually, for our purposes, assume that N equals T is the solidification time, V is the volume of the casting, A is the surface area of the casting, and B is a mold constant with units of seconds per meter squared so that the units cancel properly, so time ends up being in units of seconds. This B term, pretty complicated. It starts with the density of the metal times the latent heat of fusion of the metal over the melting temperature of the metal minus the temperature of the mold. So that's the difference between those two, times pi over the mold properties, K rho C of the mold, times 1 plus the specific heat capacity of the metal times the superheat over, once again, the latent heat of fusion of the metal, that term squared. And so this gives us the full equation for solidification time for sand casting. Now, if we start applying some values here, let's say we want to calculate solidification time for a zinc casting with the following shape, 50 by 200 by 100 millimeters. That's 0.05, 0.2, 0.1 meters. Therefore, the volume is going to equal 50 times 200 times 100 equals 1 times 10 to the 6th millimeters cubed. And if I want to get that in terms of meters cubed, I need to get my millimeters cubed canceling out on the bottom. And 1,000 millimeters for every 1 meter. So that's going to cancel only if I have it cubed. So then that's going to cancel that guy, and I'll get meters. So that gives me 0.001 meters cubed. And then the area is, I have this face and this face and this face, but then I have the other side. All of that is surface area. So the surface area is going to be 2 times each of these three faces, which is, let's start with the big one, 200 by 100, 200, 100, plus 200 is 50. What do I have next? What do I have left? 50 times 100. Math that out, it's 70,000 millimeters squared times 1,000 millimeters per 1 meter. That cancels if I have squared. That's 0.07 meters squared. So now I have the volume and the area, but I need this B. So let's start putting in some values. The density of the zinc is 7,130 kilograms per meter cubed. The latent heat of fusion for the zinc is 101,000 joules per kilogram. The specific heat capacity of the metal is 388 joules per kilogram Kelvin. The temperature of the mold, sand, is room temperature, 273 K. The K value, density, so that's thermal conductivity, density, and specific heat of the mold are 0.8 watts per meter Kelvin, 1,500 kilograms per meter cubed, and 670 joules per kilogram Kelvin. Then the superheat, the problem needs to give the amount of superheat in order to solve for the solidification time. How do we calculate superheat? That is the pouring temperature minus the melting temperature, which is the temperature going the opposite direction while it's cooling. That's the solidification temperature. So if the pouring temperature is 793 and the melting temperature of zinc is 693, then we have a 100 Kelvin superheat. Now I think I have everything to plug in my equation. Let's take a look. So B equals 7,130 kilograms per meter cubed times 101,000 joules per kilogram. The mold temperature was 273. The melting temperature was 693. 693 minus 273 Kelvin. That becomes squared times pi over 4 K rho C. 4 K rho C, 0.8. That's watts per meter Kelvin. Rho is 1,500 kilograms per meter cubed. And C is 670 joules per kilogram Kelvin. Something we should remember is that a watt is a joule per second. Joule per second. So now I have joule per second meter Kelvin over here for the thermal conductivity, the K value. Well, that's a lot in there, but I still need to put my 1 plus specific heat capacity. Started putting the units up here so that I can save space and fit it all on one line. 388 and the superheat, 100 Kelvin divided by the latent heat of fusion, 101,000 joules per kilogram, and that gets squared. Now, the fact that this term is squared and then added to 1 means that these units need to cancel out because there's no units on that 1. So if I look here, joules cancels, kilograms cancel, and this Kelvin is on the bottom of the fraction, this one's on the top, so everything cancels out. So that's good. Now I've got to look here. This term is squared, so all these units are squared. Okay, so that's kilograms. Now that kilogram, before I even square it, looks like it cancels with that one. So I end up with joules squared per meter to the 6th, it looks like, once I take care of that, Kelvin. So those are going to be the units out of there. Over here, I'm going to get joules. These are all these units are on the bottom of the equation. So on the bottom of the equation, joules squared, and then I'm going to have seconds, meters, Kelvin. I forgot this Kelvin needs to be squared. Seconds, meters to the 4th, Kelvin squared, and these kilograms cancel. Now if I look at the units here and here, I got joules canceling, the Kelvins cancel, and then I'm going to get 4 of these 6 meters canceling, and so I end up with final units of seconds per meter squared. And that's good because those are the units that I'm supposed to have for B. Now if I do the math across this, I'm going to get a B value of 3.29 times 10 to the 6th. That's my B value. Going back up here to my equation for solidification time, T equals BV over A squared. That's 3.296 times 10 to the 6th. V was 0.001 over 0.07, and that is squared. My units here are seconds per meter squared. The units coming out of here are volume over area squared, so that's going to be meters squared. So all I'm left with is seconds, and the value is 673 seconds. That is my solidification time for the sand casting.